Dear student, today we will discuss about the particle nature of light, which is called the photon, and the properties of the photon. To understand this topic, that photoelectric effect gave evidence to the strange fact that light in interaction with matter behave as if it was made up of quanta of packets of energy, each of energy hf or h nu. Is the light quantum of energy to be associated with particle? Einstein arrived at the important result that the light quantum can also be associated with momentum, that is hf over c or h nu over c. A definite value of energy as well as momentum is a strong sign that the light quantum can be associated with a particle. This particle was later named photon. The particle-like behavior of light was further confirmed in 1924 by an experiment by A.H. Compton on scattering of X-rays from electrons. In 1921, Einstein was awarded a Nobel Prize in Physics for his contribution to theoretical physics and the photoelectric effect. In 1923, Millikan was awarded the Nobel Prize in Physics for his work on the elementary change of electricity and on the photoelectric effect. Now we can in short summarize the photon picture of electromagnetic radiation as follows. So we can say that in interaction of radiation with matter, radiation behaves as it is made up of particles which are called as photons. Now we can say that each photon has energy E. Each photon has energy E that is equals to h nu, or it can be written as h c over lambda, where c is the speed of light, and each photon has a momentum that is p is equals to h nu over c, or we can say that it is h f over c. So we can write nu or f in place of frequency and speed c, that is the speed of light, and has speed of light c. So photon consists energy as hf or hc over lambda, momentum as hf upon c, and it has a speed of light. Now we can say further, all photons of light of particular frequency f or wavelength lambda have the same energy and momentum. So all photons with frequency f and wavelength lambda will have same energy and same momentum. So same energy and momentum, whatever the intensity of radiation may be. By increasing the intensity, we can see that by increasing the intensity of light of given wavelength, there is only an increase in the number of photons per second crossing a given area. With each photon having the same energy, thus photon energy is independent of intensity of radiation. So we can say that energy is independent of intensity. So photon energy is independent of intensity of light. Intensity of light. Then fourth topic that we can summarize here, that photons are electrically neutral. So photons are electrically neutral and are not deflected by electric and magnetic field. And fifth, in a photon particle collision, or interaction, we can say that in a photon particle collision or the interaction, the total energy and total momentum are conserved. The numericals of textbook as given here. So first of all we will start with example number 11.1 or the illustration number 11.1. So illustration number 1 is very simple question. The question is given that monochromatic light of frequency f is equals to 6 into 10 to the 14 hertz. So we are provided a frequency that is 6 into 10 to the power 14 hertz, that is given value, is produced by a laser. The power emitted is 2 into 10 raised to minus 3 watt. So here they have provided the power, that is 2 into 10 raised to minus 3 watt. Now the question is, what is the energy of photon in a light beam? So the first question they have asked us to find out energy. So we have to find out the energy of photon. And second, how many photons per second on an average are emitted by the source? So the second question they have asked us about the number of photons emitted per second. So this is called number of photons emitted per second. So to understand this question, we go with the condition that each photon has an energy E is equals to hf. So we can say that for answer 1 we write E is equals to hf. Now h is very well known, Planck constant. It can be taken as 6.63 into 10 to the power minus 34 joule into second. So if we put the values, that is 6.63 into 10 to the power minus 34 and frequency is given 6 into 10 to the power 14. It comes out to be, that is 3.98 into 10 to the power minus 19 joule. Now we can convert them into electron volt as well. If we want to convert it into electron volt, we have to divide it with 1.6 into 10 raised to minus 19 joule. So we can say that in electron volt it will be 3.98 into 10 raised to minus 19 joule divided by 1.6 into 10 raised to minus 19. So 3.98 divided by 1.6 gives us about 2.49 EV. So this will be energy in electron volt. Now we move to the next part of the question. They have asked about the number of photons per second. So if say capital N is the number of photons emitted by the source per second, the power transmitted in a beam equals n times the energy per photon E. So that we can say for condition B that power is n times the energy, where n is the number of photons emitted per second, and therefore n is equals to P over E. Here power is given 2 into 10 raised to minus 3 and E is given, that is, or we have find out the E, that is 3.98 into 10 raised to minus 19. So we can say that n is equals to 5 into 10 to the power 15 photons per second. So this will be the answer of the given question. So here we have completed A and B, two questions of the example 1. Now we will move toward the example number 2. Example number 2 is based on Einstein's equation of photoelectric effect. Now let us see what they have given us in the question number 2. In this example number 2, we are given that the work function of cesium is 2.14 electron volt. So they have provided us the work function. So work function of cesium is given, that is 2.14 electron volt. Now we can convert it into joule. So it can be written as 2.14 into 1.6 into 10 raised to minus 19 joule. So that comes out to be, we can say that 2.14 into 1.6, that is equals to 3.424 into 10 raised to minus 19 joule. Now we are asked to find out first the threshold frequency of cesium. So first we have to find out, that is threshold frequency, that is represented by F0. So it is very clear that F0 is equals to phi 0 is equals to HF0, and by putting the value we can get the term. Because the cutoff threshold frequency, the energy HF0 of the incident radiation must be equals to work function, and therefore we can say that phi 0 is equals to HF0. Here F0 is the threshold frequency. So F0 can be written as phi 0 over H. So Here phi 0 is obviously 3.424 into 10 raised to minus 19 joule. So we can say that this is 10 raised to minus 19 joule over Planck constant, that is written as 6.63 into 10 raised to minus 34 joule. So ultimately F0 will be 5.16 into 10 to the power 14 hertz or second inverse. So this is the value of threshold frequency. Now thus, for frequencies less than this threshold frequency, no photoelectrons are ejected. Now second question is based on Einstein's equation of photoelectric effect. What they have given? They have given that the wavelength of incident light, if the photocurrent is brought to zero by stopping potential of 0.6 volt. So we are asked to find out the wavelength of incident light. So wavelength of incident light, that is equals to lambda, that is equals to find out. So we need to find out the wavelength of incident light. To find out it, we can again apply Einstein's equation for photoelectric effect, that photocurrent reduces to zero when maximum kinetic energy of the emitted photoelectrons equals the potential energy EV0 by the radiating potential V0. Now therefore Einstein's photoelectron equation, that is we can write as EV0 is equals to HF minus phi 0. Therefore here we can say that HF is equals to EV0 plus phi 0. Now they are provided us the value of V0, that is 0.60 volt. So here we can apply the equation as per as the condition that 1.6 into 10 raised to minus 19 into 0.6 plus what we have determined earlier as per as function, work function, that is 3.424 into 10 raised to minus 19. So that will be 3.424 into 10 raised to minus 19. So when we sum up them, we can say that we have 1.6 into 0.6, that is equals to 0.96 plus 3.424, that will be 4.38. So that will be 4.384. So that is equals to 4.384 into 10 raised to minus 19 joule. Now we know that HF is equals to HC over lambda. So here we are asked to find out lambda. To find out it, we can say that therefore lambda is equals to HC over 4.384 into 10 raised to minus 19. Now H and C, that combination will give us the value, that is 19.89 into 10 to the power minus 26 upon 4.384 into 10 to the power minus 19. So when we simplify, we get the value of lambda as 19.89 divided by 4.384, that gives us the value is equals to 454 nanometer. So this is the answer that we have derived. So 19.89 divided by 4.384 actually gives us the value 4.5369, and that is near the 5454, so it will be in the term of nanometer as it is considered. So this is the value of wavelength or required wavelength. Now we will move towards the next example, that is example number 3. In this example number 3, what they have given and what they have asked, that is interesting again. In the question it is given that the wavelength of light in the visible region is about 390 nanometer for violet color. So they have given about the wavelength of light of different color. So we can say that wavelength of violet is given 390 nanometer. So it is 390 into 10 raised to minus 9 meter. Then about 550 nanometer for average wavelength of yellow green color. So lambda of yellow green is about 550 nanometer. So 550 into 10 raised to minus 9 meter, and about 760 nanometer for red color. So lambda red is about 760 into 10 raised to minus 9 meter. Now what will be the value for, they have asked that what are the energies of photon in EV at violet end, average wavelength of yellow green color end, and red end of the visible spectrum. We have to take H as equals to 6.63 into 10 raised to minus 1934 joule into second, and 1 EV equals to 1.6 into 10 raised to minus 19 joule. So first of all we have to find out energies of all these particles. So obviously E is equals to HF, that is equals to HC over lambda. We have HC as very well and fixed value, that is 19.89 into 10 raised to minus 26, because we can say this is equals to, that is E is equals to 6.63 into 10 to the power minus 34, C that is 3 into 10 raised to 8, and upon lambda, that is to be find out for different color. So here this will be 19.89 into 10 raised to minus 26 over lambda. This will be our basic equation. This will be our basic equation. Now to find out this for a different condition, what we can do now, we can apply that energy 1 or E1 for the first violet color. We can write E1 is equals to 19.89 into 10 raised to minus 26 divided by 390 into 10 raised to minus 9 meter. It gives us about 5.10 into 10 raised to minus 19 joule. Now we have to convert it into electron volt. So in electron volt, we can say that 5.110 divided by 1.6. Here 10 raised to minus 19 is common for both, so that will cancel out, and that will be about 3.19 eV. So it will be 3.19 electron volt for violet end. Similarly, we have to find out it for yellow green end. So for yellow green end, that is say E2, for yellow green end, we can say we are given lambda 2 as 550 nanometer. So we can say that is about 19.89 into 10 raised to minus 26 divided by 550 into 10 raised to minus 9 meter. So this will be about 3.62 into 10 raised to minus 19 joule. Now again, to convert in EV, we can write that is about 3.62 into 10 raised to minus 19 divided by 1.6 into 10 raised to minus 19. So this would be, as per as the condition, it will give us about 2.26 electron volt. So this would be E2 for yellow green light. And now we will go for the red color, that is lambda 3 of 760 nanometer. So that E3 will be again 9.89 into 10 raised to minus 26 divided by E3, that is lambda 3, that is 760 into 10 raised to minus 9. So this is 760 into 10 raised to minus 9, that comes out to be 2.62 into 10 raised to minus 19 joule. So that is 2.62 into 10 raised to minus 19 joule. And if we want to convert, and we have to convert in EV, so in EV it would be simply as 2.62 into 10 raised to minus 19 divided by 1.6 into 10 raised to minus 19. So here, if we compare it, this is equals to 2.62 divided by 1.6, it comes out to be near 1.64 electron volt. So this is E3 as a condition of energy obtained. Now these are different color energy in EV. Now the second question is interesting, that they have asked that from which of the photosensitive materials with work function listed in table 11.1 and using result of our energy, that is E1, E2 and E3 of A, can you build a photoelectric device that operate with visible light? So it is very clear that from the table, for a photoelectric device to operate, we require incident light energy E to be equal to or greater than the work function of the material, and thus the photoelectric device will operate with violet light. Photosensitive material, that is for sodium, potassium and cesium. So here that energy of violet light, we can say that energy 1 is greater than the energy, because energy 1 is 3.19 eV. So E1 is greater than Na, or a work function of sodium, which is about 2.75 electron volt, or we can say that E1 is greater than work function of potassium, that is about 2.30 electron volt, and E1 is greater than the work function of cesium, which is about 2.14 electron volt. Now, so this color will operate for these three materials. Another thing it is given that it will also operate with yellow green light, that is having E equals to 2.26 electron volt. So E2 is obviously, here we have E2 is 2.26 electron volt, and which is also greater than for the cesium. So it is greater than the work function of cesium, that is about 2.40 volt, 14 electron volt. So it will work with this metal, but however it will not operate with red color, because the energy E3 is 1.64 eV and will not work for any metal. For any material. So this is the conclusion of the exam.